Perfect. Thank you so much for joining us.
Thanks for having me.
Hi. And you, yes, you brought
I
one.
brought an exploded star.
I'm telling you, today is just awesome.
Yeah.
So you are the See, I'm all worked up. I have an exploded star. I have Jeffrey Osborne, visualization lead for NASA's Chandra X-ray Observatory.
Yes.
Did I get all that right?
It's a mouthful.
Basically, I have an amazing NASA scientist here. I mean, you're fantastic. You've done a ton of work. I've been super excited to talk to you because you're a leading woman in the field of science technology, which is incredible to find.
Yep.
And I think a good role model for so many women out there, for so many children out there.
Right.
So tell me a little bit about what it is that you do in a way that we can all understand.
Sure.
And then we'll go into this and some of the other stuff that you've done.
Yeah, sure. So I essentially use data to tell stories about the universe. And sometimes that can take the form of a plain image. Sometimes that can take the form of a 3D model such as this. But essentially I like to use this data to be able to help other people understand the physics and what's going on in objects like this, which is an exploded star. So that's it, in a nutshell.
That's absolutely amazing. So tell us a little bit about how it all works. So what you do with that data, how you collect it, and how it can turn into what this is.
Sure.
I mean, to think about how we're taking something from the sky and collecting it and processing it, and then how we can even compile that.
Yeah, bringing it down to Earth.
Yeah.
Yeah, so I work for NASA's Chandra Observatory, which is an observatory that was launched back in 1999 that studies the high-energy universe. So things like black holes, colliding galaxies, exploding stars, you know, pretty cool stuff. And so this observatory goes about a third of the way to the moon. And that means we have to pull down the data from afar. And essentially, when the data comes down, it's coded in the form of ones and zeros. And we have to use software to essentially translate that into the form of an image. So once we have the form of an image, we have to do many things to it. We have to process it in different ways, remove bad data, add color, because most of these images that I'm working with don't have any inherent color, specifically when they're looking at images in X-ray light. We can't see that with our eyes. So it's all about mapping, you know, visible to something that's invisible.
Wow.
Yeah.
So how do you even get involved in this? How did this project come about to you?
Well, long story or short story. My own background, I actually went to the University of Rhode Island for molecular biology. So I was studying things that were really tiny, and I ended up going into computer science, which with my physics background and the computer science background, I was kind of a perfect fit for being able to work on data like this. Shorter story is that when we get data from a telescope like this, you essentially need people that can add value to the data, that by taking the data out of the archive, by creating something from it, you're essentially creating a story that other people can then share in. So to get something like this, for example, a 3D model of an star that exploded, we had to actually use brain imaging software, because at the time they didn't have software that really fit astronomical data. So we borrowed software from brain imaging scientists in Boston.
So like a CAT scan and
MRI,
something like
type of
that?
imaging software, and a bunch of astronomers in the Harvard Astronomical Medicine Project worked very closely with the brain imaging scientists to be able to create software that other people could then use for data sets much farther away than local brains, right? Which is why this looks a little brain-like. I don't know if everybody can see it, but
am I allowed to
yeah,
touch this?
touch
I'm
it
holding
away.
an exploded star.
Yeah. So by using that kind of software and by figuring out how the star is exploding and by figuring out the velocity of the data as it's moving, you know, from you and towards you, that's how we map it into 3 dimensions. It's like using the Doppler effect, you know, the ambulance as it approaches.
Okay.
It gets louder, and then as it recedes from you, it gets quieter. It's the same thing in astronomy, except you're using light that's been either redshift or blue shifted, so farther away or closer. So that's how we create things like this, and it's great because this has, you know, scientific value. Scientists can understand their data better and differently when they can touch it and look at it in 3 dimensions. But also for non-experts, for the visually impaired, this is a totally different way to be able to look at data. And also for other learners that tend to be more tactile learners, it's a whole different way to, you know, bring the universe down to Earth.
Yeah, and that's what I was kind of my next question is, why is this important? Why is it important to do this? So you kind of just explained a little bit there. It provides another way for people to get this information.
Yeah.
But in terms of science.
Yeah.
Why is it important to be able to do this, to know this, that this is happening?
Well, I like exploded stars
It's
personally, mostly because these things are really interesting as far as they help us figure out the clues to our own existence. So when a star explodes, and stars that explode tend to be much larger than the sun, like at least 10 times larger than the sun, and they kind of, vomit their guts out all over the universe, to put it bluntly. Those guts that are going out, that's calcium, it's silicon, it's iron, it's argon, it's all the stuff that we actually use here on Earth to make, say, people and stuff. So the iron in our blood, the calcium in our bones, perhaps even the gold in our jewelry, that material is created in previous generations of stars that exploded. So for me, when we look at topics just like this, it's our own origins sort of story that we can trace and figure out what's going on. But of course, there's a much bigger picture. In general, I think astronomy is just kind of a gateway science. It's something that everybody can do. You can just look up. And the NASA program has so many amazing free resources for all citizens of the world to essentially be able to share. I think it's incredibly inspirational.
How often are you seeing this and doing this on a daily basis? Are you gathering data constantly? Are you making 3D images and 2D images? Tell me a little bit about how often and what you're working on.
So Chandra is constantly observing the universe, the high energy universe, and there are just small segments of time when the observatory is not able to observe it. For the most part, it's constantly looking at things. So we get a nice stream of data from the observatory about every 8 hours. And there's just a slew of people that actually work on that information and process it for various purposes. Getting two-dimensional data, flat images, is relatively easy, and Chandra has amazing resolution, so you get these beautiful images of our universe that we've just never seen anything before we had telescopes like Chandra. To get 3D stuff, it's a lot harder. We can't fly out in a spaceship and do a proper 3D scan of anything we want, right? So we have to do it from here on Earth. Only, yeah, I know, that'd be fun. From Chandra's orbit, and we use other telescopes as well to essentially be able to look at these objects and figure out how to get them into 3 dimensions. It's a lot of work, because these objects are far away. This thing right here is a representation of something that's 10,000 light years away, where a light year is about 10 trillion kilometers, give or take. So 10,000 times 10 trillion kilometers. Wow. That's the long, and this is close cosmically speaking. So if we want to talk about something that's even farther away, like entire galaxies, the size, the numbers get